All right. So today I'm going to give uh, kind of like an introductory crash course to quantum gates. And today I'm going to go over kind of the classical model of bits and then talk about qubits. And then I will talk about what computational basis states are and how they work. Then eventually I'll get to quantum wires and then get all the way to quantum gates. And then I'm going to try and give some examples of like how quantum gates will work on a qubit or two. And so with classical computing, just everyday computers and the computers we've had for the last like 50, 60 years, they are made up of ones and zeros. Um, and with a bit being a binary digit, that means it could be in one of two states, and then which is 0 or 1. And so this means that there's a discrete amount of states um, a bit could be in. And then the way that bits are stored in computers is it has tiny capacitors, like really, really small things that can hold electricity. And so if a bit is 1, that means that little tiny thing is holding electricity, or it means it's turned on. And if it's a 0, that means it's turned off. Yeah. And so qubits are the quantum bits that are used in quantum computers. And these are a little bit different because the state is described as a vector. So it's not a 0 or 1. It could be expressed something like that. So that would be 1 qubit. And the way that qubits can be stored inside a physical system or a quantum computer, it could be, like an atom, electron, photon, things like that. And so when we can work at the quantum level, we can work with the quantum mechanical effects and we can use that to our advantage. And so that's where we can potentially solve problems quicker and solve different problems. But this can also lead to some complication and drawbacks. And so the simplest qubits are the computational basis states, and these kind of correspond to the classical 0 and 1 bits. And so this is like right here that corresponds to 0, and this one corresponds to 1. And then also when we are writing the computational basis states, you'll see like some notation like that, and that's just called a ket. I guess that's a thing in physics, and that's what they decided to call it. And pretty much what it means is we're just dealing with something at the quantum level. And so another thing too is that we can give these vectors some amplitudes, and the amplitude is just a coefficient. So this could be any coefficient, say 0, and then like that. And so these guys right here are the amplitudes. And so you can set those to whatever you want, but we'll get to why you can't necessarily choose any two amplitudes. And so when we get to here, we can talk about superposition. And so this kind of deals with those amplitudes. And so before we go to that, so right here, if we are in either computational basis state, that means we're not in superposition. And so anytime that we use these coefficients, that will put us in superposition. And so that's just either way you could think about it is superposition is when it's not in a computational basis state, or you can, like a popular description that people like to think about is that it's simultaneously in both states, but I kind of like to more think about it as in it's in either state, and it's just kind of in this quantum state. And so when it is in that state, we can see that this would come out to be a linear combination of two states or two basis states. So like that. And so the way that we can describe this is like, let's say we'll do 0.6 right here for alpha, and then beta could be 0.8 right here. And so you could think about just have this right here. And so this would be, I don't know, somewhere right here. So this is like the vector of this linear combination. And so when it's in here, anytime in here, it's in superposition. And when it's on the line, it's not in superposition. And one thing to note is that I was saying you can't use any combination of amplitudes because the normalization constraint is put on these vectors, and that means that the probability, or not probability, if you square both amplitudes, they should equal 1. And so that means we're dealing with orthonormal vectors, which means that the magnitude of the vectors is 1. So anytime that we want to work with these vectors, we have to make sure that if we choose these two numbers, it's an orthonormal vector. And so if we go right here, just with the two coefficients last time, or the amplitudes, this would work out if we take this and this. So if we squared that and then squared this amplitude as well, this would work our way to get to 1. And so we know this is a correct vector to use. But if it was like something like this, then that wouldn't work because that wouldn't equal 1. So yeah, and so that is kind of like a little bit of the background of how the quantum bits work, the qubits, and what they kind of necessarily are. And you could just think of it as a combination of vectors. And so quantum gates, we use quantum gates to manipulate qubits and the information that they can give us. And the simplest quantum gate that we can use is quantum wires. And I'll talk about that first. And then I'll talk about some actual gates. And those are kind of some of the names. And so the simplest quantum gate is a quantum wire. And a wire is pretty much keeping the state of the whatever physical system thing that you're using. So it could be an atom, anything. And so a quantum wire is pretty much, you can think of it as some particle through the passage of time. And so right here, like this is simply the passage of time. And so if we take any basis state here over time, if we just have a good quantum wire, then the state will be unchanged. But this is very hard to, this problem is very trivial, but it's, when it comes to working with real systems, real physical systems, this is a very difficult thing to implement. And so it's difficult to implement because let's say we have some quantum wire that is stable and is deemed good. That means that the particle that we're using, its state is not so easily changed. And so when we're working with these qubits, a good example is a neutrino. And I guess a neutrino is just some particle that travels at the speed of light. But if it went through a light year of lead, it would stop, I don't know, at, it can go through lead like it's nothing. And so neutrinos don't really interact necessarily with other matter. They just pass through it. And so this is good because if we use a neutrino for this, the state is not so easily changed. And so this will come out to be that if we're using a neutrino. But the drawback to that is when these particles don't interact well with other matter, that means it'll be hard to manipulate that qubit and that information. And so while it is a good wire, it's really hard to manipulate information. And so the other side of that is if you have an unstable particle, whatever it be, the wire will be deemed not great because it won't hold this property right here. It'll be some unchanged state on the right, or excuse me, some state that is changed on the right. And so when we have an unstable state, the wire is bad, but you can manipulate that information more in that qubit. And so while it is the simplest gate, it's the hardest to implement. And so I guess when people are trying to implement that, it's just kind of like navigating that tension of having a state that is stable, but also a state that you can easily change. So yeah, and then the first gate I will talk about, probably I guess like next simplest gate would be the NOT gate. And I guess they don't say it is the NOT gate, but they just deem it as X, the X gate. And so this works exactly like the NOT gate. So down here, if you have the computational basis state of 0, it'll come out to 1, and then 1 will come out to 0. And the way these gates work they are 2x2 matrices. And so this is the matrix representation of X, or the NOT gate. And so if we do, let's say this one right here, this would come out to be 0, which is just this up here, and then 0 turns out to be this vector, and then that'll come out to be where is it? Something like that. But it'll come out to be 1. Not that. It will come out to be 1. And then this would also work on 1 as well. And so a thing to point out as well is that the inverse, if we took the inverse of this X gate, we would also, or it would be X pretty much. And so something that we can use with that is if we did XX here, which would be that, and we took these two matrices together, we would get this matrix right here, this matrix, and this is the identity matrix. And so we know that we can perform 2 knots on some qubit and it'll return it back to its original state because I is essentially just 1. And so that's kind of the first gate right there. And I'll get to why having the inverse of X being X important in a couple other slides. And so the next gate is the Hadamard gate, or just H. And this one is a little interesting because they say that this gate can induce some quantum, or like this is what actually uses quantum effects, and they don't have a precise definition of how this gate necessarily works, but the way that people like to think about it is if you take some state and did a Hadamard gate on it, then it would essentially like expand the range of the range of operations we could perform on that state. And so they say that it spreads out into superpositions. And so this will allow the computer to move in a way that you can't inside a classical computer. And the metaphor that they kind of give for this is that if you were, I don't know, if you had to cross some country But if you had to go around this giant peninsula, that would be like a classical computer because it would just have to go around. But a quantum computer using the Hadamard gate would be able to, let's say, like take a boat, so it didn't have to go all the way around the peninsula. So it's kind of like a little shortcut. And so this is the matrix representation of H right here. And then I'll also point out that if we took the inverse of H, we would also get H, and then we would get the identity matrix. And then some other gates to talk about are the Y gate, the Z gate, and the C naught gate. These are just some other ones. So these are all the matrix representations. So like the Z gate is pretty much negation. So it would take 0 and then it would give 0 and this state would turn into -1. So that's what the Z gate is for. And then the Y gate will transform some vectors, like let's say this, it could transform it into a complex state. And so we have I right there. And then like for 1, it would be right here. So you could get some superposition from that. And the C naught gate works exactly like the NOT gate, but there's a control bit and a target bit. So they like to denote it as this. So like this right here would be the control bit, and this right here would be the target bit. And so the way this works up here, this would be the control bit. And so if the control bit is 1, it'll not the target bit. And so right here, because this is 1, this changes to 1, but because this isn't 1, this is unchanged. And you could perform that on, let's say, you could perform that on 3 qubits. So something like that. And you can do a whole bunch of crazy stuff. So like you can make like this guy the control bit, and then let's say like this one, the target bit. And so this would change to that, and you can choose whichever control bits and target bits there are. And then this is kind of important. So as I was saying before, if you took the inverse of X, the NOT gate, you would get X. And if you took the inverse of H, you would get H. And same with these other gates, the Y and Z gate. And this is important because, sorry, let me back up. So the way that this works is we want to say that the matrix is unitary when you take, so this little dagger right here is the complex, or it's the conjugate transpose. And so this is a way to prove that a matrix is unitary. And so like if we took, let's say, this gate right here, which is the, I believe, sorry, we took the dagger operation, we would get 0, 1, 1, 0, and then we would take transpose and then the conjugate. So the transpose pretty much just takes the rows to columns and columns to rows, which ends up being the same. And then taking the conjugate is pretty much taking the negation of complex numbers. And because this matrix doesn't have any complex numbers, it's the same. And so if this was U right here, you'd see U dagger U, this would work out to be the identity matrix and therefore is unitary. And the reason why that we want all of our matrices, or all of our quantum gates matrices, to be unitary is because it preserves the length of the qubit. So if we did any combination of gates, and let's say we had 4 qubits, at the end of that quantum circuit of all those gates, we would want to have the length of 4 qubits in the end. And so this is really important because we really want to preserve the length of the bit stream. And this is true in classical computers. And so that's why this is really important. And so I went over classical bits versus qubits and how bits are, binary digits and have a discrete amount of states. Qubits are a 2-dimensional vector that have a continuous amount of states, and went over the computational basis states, which are equivalent to 0 and 1 in classical computing and what we can do with that. And then I talked about wires and how that can be somewhat complicated to implement, even though it is the simplest thing to implement. And then I went over some quantum gates, like the NOT gate, Hadamard gate, YZ C0 gates, and why it's important for all of the gates matrices to be unitary. And so that is the end of my talk. And then I got all this information from this really awesome paper that June recommended me. So yeah, that's all.
Thank you. Very nice presentation.
Thank you.
Yeah, your presentation is clean and easy to understand. Also, I
Yeah.
think this basic tutorial, is very important to new beginner.
Yeah.
It should
And
be very helpful to other students.
yeah. And so this made it pretty easy to understand just like the simplest things and how it works. So yeah, and then yeah, you were very right. Like this is like based on a lot of linear algebra, and so I had to go review my linear algebra and do that. So
Yeah. Oh,
yeah.
but Adam, did you have any comments?
I just wanted to say thank you for that presentation. It's good to remember the basics.
Yeah.
And I also wanted to just put an addendum on the unitary operation. From my perspective, every operation needs to be unitary so it's controllable. In other words, the whole point of the quantum computer is to manipulate the quantum states of the qubits inside the machine in a controlled manner. You don't want random variance or noise coming in and completely jumbling up your calculations to the point where they're useless. Enforcing gates to be unitary basically ensures that your gates don't do that.
Right.
It pretty much saves the information inside a quantum computer from being jumbled beyond recognition by your operations.
Your own operations, right?
Yeah. Not the operation, not like the added noise that comes from the environment. That's
Exactly.
uncontrollable.
Right. Got to control as much as you can.
Yeah. And I also wanted to say BSU is actually working on its own kind of quantum computer, and the way they're going about it is completely unique. They're not trying to get atoms by themselves to become qubits. What they're trying to do is actually, this is pretty cool to me. They're using custom DNA to assemble dye molecules which have properties in them that when activated by a specific laser basically become have parts of them, specific particles in the dye molecule that become quantumly or quantum entangled with each other, and you can control the entanglement of those molecules using the laser. And basically the molecule itself acts like a stabilizer. It prevents the external environment from manipulating the two particles inside the molecule that are entangled with each other in the laser.
Oh, so it's like they're not working with like individual atoms, they're working with straight molecules.
They're working with particles inside the molecule using a specific kind of laser. a laser that can change frequencies at an extreme rate.
That is crazy.
Yeah, they're building DNA, which then transcribes RNA, which then uses ribosomes to create molecules, which are then put into a laser to become quantumly entangled. That's the project.
Oh.
And BSU got $10 million worth of funding from the National Science Foundation to work on this.
Do you know where they have it?
The labs, it's not where they have it, it's where they have the other labs. It's a bunch of smaller labs working together. One of which
Gotcha.
is, there's actually 5 labs working on this, one of which is the computational simulation lab, but they're not actually based here. They're based in the engineering department.
Right.
What's odd is I looked at the professors and PhD advisors and students working on this project, and I don't think there's anyone from the CS department working on this.
Right. Yeah,
Which
because
I
it's,
find,
well, they're
I
probably not
find,
trying to write anything. They're just trying to like build the dang thing, huh?
yeah, but what I find odd though is they're trying to use simulations to model this process before they commit to anything specific.
Right.
So that's actually one of the cornerstones and one of the reasons why they got the NHS funding in the first place. Because they had simulations that proved that this method could be used in the real world. In other words, based on our best models, it isn't complete bogus.
Right.
And we have a chance of making this work.
Oh, you mentioned the simulation. So they just simulate this process in a computer, or
Mhm.
they test this in some quantum machines?
They don't test it on a quantum computer. They use quantum simulations to do this, but from all the they simulate the entire end-to-end process. They simulate the construction of the DNA transcribing into RNA, that RNA then being used to make the molecules, which are then put into like a simulated laser. They simulate the entire process, beginning to end,
Okay.
and that's how they got the funding. It's kind of a crazy idea.
Right.
They're using DNA and biological processes to create a quantum computer.
Yeah. Wait, so you're saying they use like that simulation to get the grant or whatever?
They use the simulation
Gotcha.
to get more funding.
Right.
What's interesting about all this too is that they're also trying to do this to see if they can make a physical model that they can use to test if quantum processes are being used by living organisms to speed things up or make things possible. The whole basis of this idea is to test if the photosynthesis process actually uses quantum mechanics to work. And they're basically trying to artificially reconstruct those dye molecules found in plants for photosynthesis. And they're basically simulating the manipulation of particles in those dye molecules using that laser to mimic
Right.
what they believe are the quantum processes inside photosynthesis.
Okay, that
It's
idea sounds
crazy.
interesting. Oh,
It's
which
crazy.
department again?
What was
Sorry,
that?
what? You said this project is not come from our department. It is other department in the College of Engineering. Okay, I see.
Mainly computational biology and quantum and computational quantum mechanics people.
Oh, okay.
Those are the ones that assemble the simulation.
Hmm.
The guys that assemble the simulation.
Right.
So they like have a CS and biochemistry background.
Yeah, 5 million grant from the Department of Energy.
Yeah, the
Yeah.
Department of Energy is
Phase
also
2.
funding it too.
Yeah, a renewal grant.
Pretty cool project, got to admit.
Yeah,
I'm hoping it generates something useful.
something. Yeah.
Yeah, thank you for sharing this.
Yeah, it's a big BSU project, by the way. It's one of the biggest ones I think the university's worked on. And here, that's it from me. Do you have anything else you want to say, June or Jack?
I don't have much.
Yeah, I
That
don't.
sounds really interesting.
Yeah, just say thank you to you, Jack. Good presentation.
Thank you. Yeah, I hope it was, kind of well
Enlightening.
together and flow. Yeah, just kind of good reminder for everything.
Yeah, also it's good practice to brave the podium and talk about something you're unsure about.
Yeah, definitely. That was good. So, but yeah, I don't think I have anything much to say.
Okay, I will stop recording here.